the Zeroth law of thermodynamics. Yep, you heard that right, Zeroth. It's the law that somehow had to come before the first law, and trust me, the story behind its name is just as cool as the science itself. I mean, think about it. First law, second law, third law, that all makes perfect sense. It's a nice, clean order. But Zeroth? It just sounds wrong, like a typo or a placeholder they forgot to change. But as we're about to find out, that odd name was actually a really clever fix for a problem that popped up way later than you'd think. So to really get a handle on this law, we've got to start with that name, because the story here isn't just about physics. It's about the messy, human way we figure things out, sometimes out of order. So check out this timeline. By the middle of the 1800s, the big guns, the first and second laws of thermodynamics, were already on the books. These defined huge concepts like energy and entropy. Then, almost a century later, in the 1930s, physicists realized, there's another principle that's so basic, so fundamental, it really should have come before all of this. But you can't just go back and renumber established laws of physics, right? So they came up with this brilliant, elegant solution. They just called it the Zeroth law. That way, it could slot right into its logical place at the very beginning, where it belonged. Okay, so that's the why behind the quirky name. Now let's get to the what. To understand what the Zeroth law is actually saying, we first have to wrap our heads around one super simple core idea: thermal equilibrium. Now, that definition sounds a little technical, but the only part you really need to focus on is no net flow of thermal energy. Just picture this. You pour a hot cup of coffee and set it on your desk. At first, you can feel the heat flowing from the mug into the table. But after a while, that stops. When it does, boom, they've reached thermal equilibrium. And that's really all there is to it. Thermal equilibrium is just that moment when two things in contact with each other stop trading heat back and forth. Why? Because they've reached the same temperature. It seems so obvious, right? But this simple idea is the entire foundation for the Zeroth law. So let's get to the law itself. And I promise you, this is going to feel very familiar. If you can remember anything from your old math classes, you know that transitive property thing, where if A equals C and B equals C, then A has to equal B? Well, the Zeroth law is basically that exact same logic, just applied to heat. And there you have it. That's the Zeroth law in all its glory. The official wording is a bit formal, sure, but the idea behind it is actually incredibly simple and intuitive. Let's just break it down. Okay, let's walk through this together. Imagine we have three objects. Let's call them A, B, and C. Now, if object A is in thermal equilibrium with our third object, C, meaning no heat is flowing between them, and if object B is also in equilibrium with C, well then the law guarantees that A and B must be in equilibrium with each other. They have to be at the same temperature even if they've never actually touched. C is basically acting as a trusted go-between, and this simple logic is what allows us to compare temperatures at all. At this point, you might be thinking, okay, that's a neat little logic puzzle, but what's the big deal? Well, this is the payoff. This one simple rule is the entire reason we can measure temperature. It is the absolute fundamental principle that makes every single thermometer work. I'm serious. Every single time you've ever used a thermometer, whether it's an old mercury one or a fancy new digital one, you are using the Zeroth law. Without it, the very concept of a consistent, reliable temperature scale wouldn't have a scientific leg to stand on. It's that important. So let's connect this right back to our A, B, and C example. When you take your temperature, your body is system A. The thermometer is our trusted middleman, system C. You put them in contact, they reach thermal equilibrium, and now the thermometer's reading reflects your body's temperature. And because of the Zeroth law, we know that thermometer can now reliably compare your temperature, A, to anything else, like the outside air, which we can call B. The thermometer becomes a universal translator for heat. And this goes way beyond just thermometers. This fundamental rule is like the invisible engine running behind the scenes in countless technologies that we use every single day. Just think about your thermostat. What is it really? It's a thermometer, our system C, that's constantly comparing the air in your room, system A, to the temperature you've set. Your refrigerator, your oven, your air conditioner, they all work on this exact same principle of measuring and comparing. It is the bedrock of any technology that needs precise, reliable temperature control. So what seems like a statement that's almost too obvious, that things at the same temperature are, well, at the same temperature, is actually the critical foundation for all the comfort and convenience we completely take for granted in our modern world. And that really brings us full circle.
The Zeroth law might have gotten its weird name because of a historical accident, but its place at the very, very beginning of thermodynamics is totally deserved. It gives us the solid, logical foundation for the idea of temperature itself, which allows all the other, more complex laws to be built on top of it.
So the next time you adjust your thermostat or check the temperature outside, just give a little nod to the humble, quietly brilliant zeroth law. And it really makes you wonder, doesn't it? What other simple, obvious truths are out there, silently holding up entire fields of complex science?